My LinkedIn is archaic.
I know, I was like, weird, should you recommend me? Sure.
Literally every single morning I wake up with a video.
About me.
Yes.
So odd.
I know, and then there's like your little picture. Oh, fun. That's great.
No.
I saw the little fire
I was
thing.
like, what? I haven't made.
What'd you do?
Yeah. And I'm actually like, put myself again. I literally didn't get there until this episode.
It's recommended. Yeah. I'm trying to make a blood go somewhere else.
Oh,
I think I need to take a nap after what's happening in it.
Let's just all the good vibes and one thing off the last. Yeah.
So for,
But then you're like,
I know. Yeah. It's just how. Good afternoon. Did we leave off with the last time? Started to talk about, what did we leave off with, was the big thing? Eta, right, eta squared. So we'll recap that a little bit, but really important that we get that eta squared. So we defined it as eta SS between over SS total. And we called eta squared a measure of effect size. Effect size, right? It was an effect size. So eta squared is similar in respects to Cohen's d. They're both effect size measures. They're both effect size measures. So we'll recap that a little bit and continue on with analysis of variance before the break. And then after the break, we'll go over some of the assignment 2 questions, a little bit of prep for the midterm next week. Cleaning up, chapter 2. So you gotta clean up a little bit. Just talk about confidence intervals. a little bit. That's part of what assignment 2 is, or filling some of those gaps. Well, what's a confidence interval? What's a confidence interval? Well, there's the formula for it, but the way for the 2 sample case, one mean minus another mean, but the way to think of a confidence interval is like this. So over here, I have P, that's the parameter, okay? That's the parameter. What's the example of a parameter? Let's give an example of a parameter that I want to estimate. Yeah, say like a mean, right? I want to estimate that parameter. So up on the board is the mean. Maybe the parameter, what's the parameter up here? Over here. What parameter do I want to get at? I want to get at the mean difference, because this is for a 2 sample case, so I may want to estimate that mean difference. So we know that statistics are all about estimating parameters. Want to estimate the parameter, okay? So I stand over here, and there's the parameter over there. I'd like to estimate that parameter. Well, that parameter is in the population, so I don't have access to it, right? You know I don't have access. I usually don't. When do I have access to it? I have access to it if I have all the objects, right? If I have all the objects, I know the parameter. Estimation is irrelevant. Still some measurement issues potentially, but estimation is irrelevant. So I see the parameter, I get, what do we call this thing? An estimator, right? I get an estimator. What's that estimator gonna be? Well, it could be the sample mean. Probably a better estimator than what? The sample median, right? Because that's the population mean. So I get the sample mean, okay? So you picture in my hand, I'm using the sample mean, and I'm gonna use the sample mean to estimate mu. Sorry, let me just go with y, because we've been using y a lot. So there's the mean of y, I'm gonna use that to estimate mu, okay, to estimate mu. We know that the expectation of the sample mean is equal to the population mean. Okay, so we know that, we talked about that a little bit. It's an unbiased estimator, it's a good estimator, and on average, in the long run, this is actually gonna get to this, okay? It's gonna get to this. However, if I take this sample mean, so imagine I got the sample mean, and I throw it at the parameter as an analogy. I throw it right at it, okay? So here's my sample mean. Going through like this here. Okay, what's the probability that it's gonna hit the parameter? Let's think about that for a second. So I've got my estimator, got my sample mean in this case. I could be a different estimator for a different situation, but in this case I'm gonna use the sample mean. So I use my sample mean as an estimator of the population parameter. The question is, what's the probability that this is gonna hit on any given estimation? Well, what's the value of my parameter? Let's give a value for it. Okay, so the value of my parameter is maybe equal to, let's just pick a number, whatever we're dealing with, but let's say 100.0. Okay, 100.0. Do you think that when I calculate a sample mean on a sample, that sample mean is going to be a match to what the parameter is? Probably not, right? Probably not. And we could even say highly probably not, right? Why? Because this sample mean, I mean, let's compute a sample mean. We compute the sample mean, say comes out to be 98.2. Well, that's not gonna hit. Another sample mean's not gonna hit, etc. And even if I did get 100.0 for the sample mean, well, this probably has more decimal places, so I could always carry more decimal places. In other words, this attempt, almost like if I'm like throwing the spear to it like that, like that, this going through is not gonna hit. It's not gonna hit. The expectation in the long run, right, the average of all these sample means I could get is going to hit. That's okay, and this is still true. But on any given estimation, that's not gonna hit. So if that's not gonna hit, let's think about this very intuitively. That's not gonna hit. This is my estimator, so it's not gonna hit. Right there it is, like that, just so we set it up here, like this. Oh, it didn't hit again, it didn't hit again. What do you suggest we do? This is too what? Too narrow. this is too narrow. What if I did this? I said, you know what? That's not gonna hit. Give it a break, right? Give it a break, do this. A little bit wider, a little bit wider. Allow a little bit more flexibility in the estimator, right? In the estimator, allow a little bit more flexibility so that you provide a little bit wider of a range of values that may capture that population parameter. Does that make some sense? So I do this here. Okay, I widen it a little bit and then I throw it at the parameter. Imagine like you're estimating throwing it at it. It's kind of a good analogy. You throw it at it, then you ask the question, what's the probability that this is gonna hit? It's probably higher than if it's like this, right? So here's one example, it's coming through. Oop, caught it right there. Another one, ooh, just missed it. Another one, caught it, missed it, caught it. So then I go, wow, this is good. Producing an interval estimator, an interval estimator. The interval is now what I'm using to do the estimation. It's not just one particular value, it's an interval. We could think of the one particular value as being what? An extremely, extremely, extremely small interval, if we really, really wanted to. Usually don't. We say that's a point estimator, use an interval estimator. Okay? You'll have a higher chance of capturing it. So let's take this to the extreme, right? I'm kind of exploring this idea and I say, wow, if I do this, I have an increased chance of capturing the parameter. Well, what am I tempted to do? I go, I get an increased chance. Take it and make it wider, right? Make it wide, say, well, I can get the hang of this. Do this, right? It's like when you come home from work and your spouse hugs you, you got a better chance of capturing you if you're like this. Right? Nobody hugs like this, right? They'll miss you, or they'll hit you, right? So then, you know, you say to your spouse, I want to make sure I really hug you today, right? I want to make sure. It's the same concept, right? What do? How do you approach your spouse? What would be the best way? And grow infinite arms, right? Grow infinite arms this way, and what's the probability that you capture your spouse? 100%. 100%. So it's tempting to take that interval and to make it wider. Making the interval wider is going to increase the probability of capturing what you're after, okay? So making the interval wider will increase the probability of capturing the parameter. If you make it too narrow, what happens? Eventually you get to the point estimate, and we could say that the probability that you'll actually capture it kind of goes to zero because it's so narrow. As we're saying, you throw the mean at the population parameter, no, it's not going to hit. This range of values, this interval estimator, okay, so let's write that down, this interval estimator, it's an interval estimator now. Interval estimator is very common in statistics for the reasons that we're talking about, that it gives you a higher chance of actually capturing the parameter than if you use the point estimator. So we're going to call these interval estimators by the name of confidence intervals, okay? Confidence intervals. And what's a confidence interval? Well, let's use the language of probability. We've been talking about the idea of probability here. We have a lower limit, there's a lower limit, there's an upper limit, right? There's an upper limit. This is theta, this is the parameter that we're after. Okay, so theta is the parameter we're after. Different sources use different things for parameter names. You can call it whatever you want, but we just use that language theta, which is what Montgomery uses. So there's theta, and we say the probability that theta is between those two limits, right, is between the lower limit and the upper limit. The lower limit and the upper limit is equal to 1 minus alpha, is equal to 1 minus alpha. So what we're going to construct here is The idea of a confidence interval, this interval right here, that's up here, that has a probability of, what's that interval communicating? Is the probability of containing the parameter, right? You're building an interval that has a probability of containing the parameter. That's called a confidence interval for the parameter. It's called the confidence interval for the parameter. So let's just, before we look at one example of a confidence interval, let's think about what's going to determine, what's going to determine the width of it. Well, if you take, let's take a 95% confidence interval. So let's say we have a 95% confidence interval. We're going to make a 95% confidence interval. So what can we say? Well, if it's a 95% confidence interval, then the interval we build has a 95% probability of what? Capturing the parameter, right? Of capturing the parameter, of catching it. Okay. So let's think about this. You have a 95% interval. What's going to determine how wide that interval is, right? What's going to determine how wide that interval is? Well, let's look at the case for the t-test. So here we have a 2-sample t-test. You can do it for 1 samples too, but here's a 2-sample test. And I just want to note too that in the book, you'll see this notation sometimes, mean 1 minus mean 2, and then you see minus population mean 1 minus population mean 2, okay? That's the most complete way to write the independent samples t-test. And what that's saying is, you might want to hypothesize a different difference other than 0, right? So if you assume that there's already a difference between mean 1 and mean 2, you could actually include this in here. So you're saying, this mean minus this, whatever we specify that as under the null, but 99.9% of the time, and what computer software is going to assume this is equal to what? 0, right? This is equal to 0. So that's why the t-test really comes down to mean 1 minus mean 2. You don't have to put that extra stuff, but just realize it's there. It's not going to be on the test. You're not going to see it again, but just realize it's there. Okay. So we've got our t-test. We've got our, there's our pooled variance. We've got our standard error of the difference down there. We say it's distributed as t, right? It's distributed as t on those degrees of freedom, okay? On those degrees of freedom. So again, just to, some of this is a review for the midterm too, is distributed as t. We know what that means, right? Distributed as t. Well, that's distributed as t because what? Well, you're using the pooled variance in the denominator. You don't know what the population variances are, so it's distributed as t. This thing has a t distribution on those particular degrees of freedom. So let's look at that t-test and see how we can actually build an interval around it. Well, there's a couple ways of putting these statements. The second way, which I've listed down here, this is all one formula, is the way we're going to most often think about it. But let's look at what this says, right? This says up here, the first formula, let me circle the first formula because they're almost overlapping. This formula right here says that the probability that this t, right, this is the t that we're computing, it's right in here, the probability that that t is greater than or equal to a negative t critical value, that's the negative t critical value on the lower end of the curve, and this is the t on the upper end of the curve, so the probability that that is between those values is equal to 1 minus what I said alpha hat. So this saying, what's the probability that the t you obtain is between the negative critical value and the positive critical value? What this translates to is more in line with what we're talking about with estimating the parameter, is there's our parameter, right? That's the parameter difference in this case, but this is what? This is theta, right? That's theta. That's the parameter we want to estimate. Just because it's a difference, don't let that bother us. It's the parameter, it's the difference between means. If I wanted to estimate one parameter, I could just say, well, I'm estimating the parameter like the mean. This is the difference between means, but it's the parameter we want. So we say that the probability right here that mu1 minus mu2 is between, what's all this stuff? It's between this side of the equation and this side of the equation. So these are going to be our bounds, the lower limit and the upper limit on the equation. So here we have, this is all the lower limit, that's L, and this is all going to be the upper limit over here, that's the upper limit, okay? Now when you look at this, well, what's gonna determine if I compute a 95% interval, so if I set my alpha at what, 0.05, this is gonna be 95%. So if I compute a 95% interval, so I say, I wanna compute a 95% interval, well, what's gonna determine some stuff here, right? What's gonna determine some stuff? Well, the same kinds of things that happen with our n in the significance test, right? In the significance test, the same types of things are at work. So I'm gonna compute a 95% interval, and I'm going to do what? I'm gonna collect as much data as I can. I'm gonna collect as much data as I can. What's gonna happen? I'm computing a 95% interval. What's gonna happen to that interval? Is it gonna be wide, or is it gonna be narrow? Well, think about it, right? So it's a 95% interval. What would we like to say more? I'm 95, we'll just use this loosely, but I'm 95% confident that the true mean or mean difference or whatever parameter is between here, or would you like to say I'm 95% confident that the true difference is right in here? Yeah, what's better, right? You want to be as precise as you can. You want to be as precise as you can. So narrow confidence intervals, contrary to this idea, right? Contrary to this, are actually nice. We like narrow confidence interval. When we say a confidence interval is fairly narrow, what does that mean on the street? It means, you know what, you're estimating it pretty precisely. That's pretty good. No, the mean weight loss for people on the program is like 10 pounds, give or take half a pound, plus or minus half a pound. Well, that's a lot better, right? That's a lot better from a research standpoint than if I said what? Well, the mean weight loss is 10 pounds, give or take 20 pounds this way, 20 pounds this way. Kind of like, what are you saying as a researcher? I don't really know where the mean difference is because my range is so wide. Okay.
What's setting that, two questions.
Yeah.
So the 95% refers to a probability, not a width of the interval.
Well, there's two things, right? That's a good question is, what is the 95% referring to, right? What is the 95% referring to? You can have a 95% interval that refers to the 95, we're gonna discuss the exact meaning of that 95% probability, but it's the width of that interval that, with the numbers that you use, that's gonna determine what your 95% interval is. So it's entirely possible that I have a 95% interval, it's not very good, it's pretty wide. It's entirely possible that I have a 95% interval that actually has very narrow estimation. If you think of the, if it comes down to the variability, right, the variabilities. If your variabilities are low, maybe your sample size is large, you're getting a pretty narrow estimate, even if you're computing a 95%. Even if you're computing a 90%, you're getting it to be fairly narrow. So the 95% interval, when we say, well, I'm gonna compute a 95% interval, the exact numbers that you get are gonna be determined by your sample size and by your variances and how precise things are, Now, what if I decided, well, go back to my original strategy. My original strategy was what? My original strategy is what? Well, how about I just widen the interval myself? How about I just widen the interval myself? Well, if you widen the interval yourself, yeah, you take 95%. If I go towards 100%, well, yes, I can be 100% confident, and that's just gonna give me very, very, very wide bounds, which isn't very, very good, right? Which isn't very good. So we like about 95%. Sometimes we use 90% confidence intervals. What's a 0% confidence interval? If you really, we don't compute 0% confidence, but if we were to talk about it, say, theoretically, what would be a 0% confidence interval? Well, the probability that I capture that parameter to have a 0% chance of capturing it, what would it have to be? Would it be this? Nope. Right down to my point estimate. Right down to my point estimate, which is that first case that we talked about. If the point estimate, we could kind of say, no, there's your 0% because that thing's never, this is like sliver, this is like a sliver. You're throwing it at that, that's never gonna capture it, it's never gonna capture it. So as I go wider, well, this is what happens, I do this. Okay? So let's define what the confidence interval is. Let's give a precise definition as to what it is, and then when you compute it on your data, it'll be narrow, it'll be wide, depending on what your data numbers are. Understanding how to define the confidence interval can be a little bit tricky, and we have to go over a couple interpretations of it. So let's brainstorm it. How should we define it? How should we define the confidence interval? Well, we said it's the probability, right? It's the probability that the parameter is between that lower limit and upper limit. But I don't know, what does that really mean, right? What does that really mean? So confidence interval definitions or interpretations. So I'm gonna say 95%. Say I got a 95% confidence interval. What could that possibly mean? Well, we said there's 95% probability that the true parameter is between the upper and lower limit. Upper and lower limit. So I've got my parameter, and I've got my lower, and I've got my upper here. Now, there's a little bit more to the definition than that, and here's where it gets kind of weird. 95% confidence interval, when I compute that on my sample, okay, I've computed one interval. Okay, I've computed one interval, one 95% confidence interval. Okay, so let's say that my true parameter that I'm seeking to detect is right here. And this is analogous to like what we have here. Just imagine this is like a straight line, okay? So that's the parameter value. Let's call it the let's just call it theta. There's the parameter value. I'm gonna collect the sample, and then I'm gonna build a confidence interval. Okay, so I'm gonna collect the sample, I'm gonna build a confidence interval. So let's look. My first sample, S1, is right here. This is my first sample. Get my sample, my mean turns out to be less than the parameter, turns out to be over here. So this is where it ends up being, right here, in terms of estimating. Does it make sense? Okay, so I've got that. Now, am I off from my true parameter? Yes, I am. Does it surprise us? No, it doesn't surprise us. We know that thing's not, that's like, boy, that's like a 0% right there. So I say, well, I'm gonna build a 95% confidence interval around that sample mean. So I build it, and it does this. It does this, okay? So those are the limits. It goes out this far. So this plus a certain amount minus a certain amount. And most of the time they're gonna be even amounts on both sides. Okay, you're always gonna be building equally sized intervals on each side. Did it capture it? Yes, it did. It got it, right? Look, it caught the parameter. It caught the parameter. That particular confidence interval that we computed was successful in capturing the parameter. It caught it. Even though the actual point estimate happened over here, it caught the parameter. Okay. I'm gonna do another sample. So I say, well, that's great. I'm gonna collect another sample. I collect another sample. So I get, instead of sample 1, I get sample 2. There's my mean. That one captures the parameter. That one captures the parameter. Again, I do it again. So I do it again. And what do I get? Well, this one actually was really nice, because it's almost towards the center of it. That one captures it again. I do it again, I do a few more, capture, oops. That one missed it. There's my mean there, means are all that center. There's my confidence interval for that particular sample, and what can we say about that particular confidence interval? Do we get it? Nope. In other words, the hug that 95% of the time when you come home, this hug does it, right? What can I say? There's gonna be some times where what? It doesn't do it. How many times? 5% of the time. 5% of the time, this hug is not gonna capture this mouse. 95% it is. So what I've done is I've said it's a 95% confidence interval. You can see that the 95% confidence interval has, what does this kind of remind you of? One sample, another sample, another sample, another sample. Relative, when I take all the confidence intervals and I count how many times does it actually work? Right? How many times does it actually work? If I continue doing this over and over and over, how many times, at least in theory, would it work? How many times would it work? How many times would it capture? How many times do you hug your spouse? 95% of the time. 95% of the time, right? This has what type of probability meaning? It's like a probability, right? Because you're like, you keep computing intervals, new sample, compute an interval, new sample, compute an interval. 95% of those samples is gonna capture the parameter. How many samples should you collect? Infinite number, right? Let's go for an infinite number. And then let's take the number that capture versus the number that don't. So if it's the number that do, not the number that don't, versus the total number, then we've got a relative flipping heads, 95 heads, relative frequency. It's a relative frequency. It's a relative frequency because I've taken a frequency, at least theoretically, right? I've taken a frequency, at least theoretically. I said, you know, if you continue doing this over and over and over and compute new intervals on each sample, then 95% of the time, you're gonna capture the parameter, right? You're gonna capture the parameter. This is how the purists like to interpret confidence intervals, and some of the best writers on the subject, even they report it like that and they say, this is kind of awkward and confusing and weird, but this is how we define it, okay? And if you think about it, it's kind of, what's the problem with it? Same thing kind of, you know, like here's one interval, here's another one, here's another one, here's another. Look at what the mean is doing. The mean's here, the mean's here, the mean's here, the mean's here, the mean's here. In one way of looking at this, do we have any idea where the sample mean is? Not really, right? Not, it's like, boy, what if we demonstrated that we don't know anything, right? What we've demonstrated is that I'm not quite sure where the mean is. So when I calculate one sample and I say there's a 95% bounds on here, boy, that doesn't even seem right anymore, because when I compute the next one, it's probably gonna move. It's probably gonna move. So what authority do I have to say that the true mean is within these bounds, right? What authority do I have to say that the true mean, the true parameter, is somewhere between here, right? So that confidence interval is giving us a range of values, plausible values for the parameter, right? Range of values for the parameter. So let's put that down. It's the range of values. Plausible, we can say, plausible values for the parameter. For the parameter. For the parameter theta's plausible values. So if I look at one confidence interval, and it's, you know, this one right here, these are plausible values for the parameter. Does it include the one that I'm trying to capture? Yes. But nonetheless, what is this confidence interval basically saying? You know, the parameter value could be kind of anywhere. In other words, us thinking that it's like right here, yeah, that's a plausible value for the parameter, but so is this one, so is this one, so is this one, and actually, that one actually does a lot better than this one right here. So plausible values for the parameter. So to bring this down to real life in the weight loss program, say, you know, the average weight loss is 10 pounds, give or take 2 pounds. What does that mean, right? Let's interpret that. So, you know, I gave the pill to people, and 10 pounds, give or take 2 pounds. I'm not quite sure where the parameter is. It's somewhere in there. My estimate in the sample says 10, but really it could be between 8 and 12. How many people voting for Biden in the poll? Margin of error. Well, it's, you know, what do they say, right? 52%, give or take. And when they say, well, give or take falls within the margin of error, that's the kind of thing they're talking about, is that uncertainty, kind of going, you know, we don't, it's somewhere there, but we don't know, we don't quite know where it is. We don't quite know where it is. How's my magic pill doing? Give the magic pill, it increases their IQ points by 20 points. Give or take, what sounds better? Give or take half a point. Wow, that's really good. If I get a 95% interval, and 95% confidence interval, and the margin's half a point, wow, what precision. But if I set a 95% interval, and I don't know, they're somewhere between 20 points and 10 points and 30 points all over the place, then I haven't really estimated what's the word? Very precisely, okay? So let's just look at this and see, does this make any sense? Well, what the 95% confidence interval is saying is literally this, relative frequency interpretation. Okay? So we can say, let's just put it over here, in 95%, okay, in 95% of samples, in 95% of samples, the computed confidence intervals, okay, capture the parameter. They capture the parameter in 95% of samples. In 5%, they don't. They don't. But the issue with this is that on each sample, I'm computing a new confidence interval. Okay? On each sample, I'm computing a new confidence interval. So what the purists like to say is they like to say, you know what? This has nothing to do with this particular interval. This has everything to do with, here it comes, the method of computing confidence intervals leads us to conclude that 95% of samples, the computed confidence interval will capture the parameter. So they like to refer to it as the method. And what's the method here? Right? What's the method? The method is collecting the sample, computing what? Your standard error, constructing a confidence interval, and saying there's the confidence interval. This method, 95% of the time, will work in capturing the parameter. Okay? Now, is that satisfying? What are you going to go tell your supervisor when you do an experiment? You're going to calculate a confidence interval, and they're going to say, oh, so the supervisor says, oh, so you're saying that the true mean looks like it's between these values? You say, hold on, all right? 95% of intervals will capture the true parameter, but this refers to the method of computing confidence intervals over repeated intervals. So in other words, supervisor, this interval will likely change when you do it again, when you do it again, when you do it again. So what does your supervisor ask, given that? You say, then where the heck is the mean? If it's gonna change all the time, then what if we really kind of determine? It's like saying we're not quite sure where the mean is. So if I get bounds on this, and let's put some numbers here, 100, and this is 98, let's say that that's what the interval works out to be. and then let's say this is 102. Let's give an interpretation to this. It's a 95% confidence interval. The limits of the confidence interval are 98 to 102. Let's see if we can work on an interpretation of that actually makes some sense. What could we say? What could we say? I mean, look, if you go back to this, you did the experiment, you did one experiment, and it gave you this. The IQ, 100, you're estimating Montana IQ, and you get a confidence interval of 102 to 98, the mean is 100. What could it possibly mean? How do you interpret it? You know, like, are you gonna go to here? Or are you gonna say, well, how does this help us, right? How does this help us? In 95% of samples, the computed confidence interval captures the parameter. Do you care about 95% of samples? No, what do you care about? You care about what your sample did. So we can go back to this. Does this help us? Plausible values for the parameter. Plausible values for the parameter. 100, 98, 102. All of these values here are plausible values for what the parameter is. The estimate is 100, but these are all fair game as well. If you interpret it this way, and you accept the relative frequency interpretation, you get into a situation where it's kind of hard to figure out, well, what is it actually telling us? What certainty is it telling us if the interval is gonna change each time we compute a new sample? So wouldn't it be a bummer if you had to tell your supervisor, yeah, but this is only based on our one sample. You know, if you get another sample, it could be way over here. And it could be over here, and it could be over here, which would seem to not provide very much certainty over what the darn population mean is. So this definition here is a good definition for research-wise in terms of trying to get the precision on the parameter. Sometimes researchers will also interpret it this way. They'll say, you know what, there's your bounds, 98 to 102. If you get another sample, it's a pretty good chance that it's gonna be between those bounds. It's a pretty good chance it's gonna be between those bounds. And that's a nice way to help understand it from a research perspective. Because it's fairly obtuse understanding it simply by the 95% of sample argument, even though formally that's what it means. Does that make some sense? Okay. Confidence intervals are not extremely intuitive, especially when you have to bring in that relative frequency, but we know what they are intuitively, and you have a distribution, and you say, there's my mean, there's my lower limit, there's my upper limit. I'm pretty sure the true parameter is between those points. Okay. Makes some sense. Yes.
So this is only for the parameter. This really doesn't say much about the actual, I mean, I guess it does say something about the population.
Okay, so good question, right? Is this about the parameter, is this about the population? Well, you're estimating the parameter. You're estimating the parameter, right? And these are how the confidence intervals that you compute will behave, assuming that the parameter is something that's known out there, right? So the parameter is, we assume that the parameter is fixed. We assume that there's a real parameter of IQ for Montanans in the population that exists before you even start the study. What you're trying to do is you're capturing it. You're trying to capture it. So all of these are like, some authors refer to it as horseshoes. Does anyone play horseshoes anymore? Horseshoes, yeah. So horseshoes, right? You got the ring and you're like, is this gonna capture it? Is this gonna capture it? And you're using a 95% confidence horseshoe, then 95% of those are going to capture it, But the thing is when you look at it like this, and this is what you get from your experiment, you want a way to interpret this. You don't just wanna say, hey, in 95% of intervals, I will capture the population mean, because maybe your interval happens over here. So you calculate this, do you have any confidence that it's between 98 and 102? It would seem not, because maybe in your next sample it would be over here. So you say, where's my confidence? Well, that's where they like to say the purists. Right? Like to say the method, it's the method that you're doing. But practically speaking, on that one sample, that's all you got. You're not gonna compute an infinite number. And on this, you gotta say, you know what, our best bet is that it's gonna be over between here. So, what intervals are computed usually in research? It's usually 95%. 90% sometimes 99%. But once you have your computation, remember that as if you go to 100%, well, you get wider, but it doesn't become very useful. So that's where that works, but usually it's gonna be about 95% intervals. So you're gonna see 95% intervals, you know, probably forever, and maybe you might see like a 99%. Okay, so that's confidence intervals, and we'll recap that a little bit regarding the question on the test. The other thing I want to talk about is just to describe the degrees of freedom issue. The correction on the degrees of freedom. One of the questions in the review has to do with the, what is it, unequal variances. So if you have unequal variances, what's the instruction? Well, if you have unequal variances, you should do an adjustment on your degrees of freedom. So you shouldn't compute the good old t-test, you should compute an adjustment. So if I put the two sample test, so there's my t, mean one, just put it back up, and I've got my variances here. So this is a two sample t-test, and the question is, well, the question is if your variances are unequal, right? If your variances are unequal, now how unequal do they have to be? Well, we assume, a null hypothesis is that variance one is equal to variance two. Variance one is equal to variance two, okay? And I can't quite remember if last time we described a rule for this, kind of a general rule for your variances. Well, how do you determine if this is true? Well, all you have population variances? No, you only have sample variances. So this refers to population parameters. So you look at your sample variances. This is the best thing you have. So you've got 1 and you've got 2. And let's say this sample variance, just make up some numbers, comes out to be 10. And this one comes out to be 5. So one variance is equal to 10 and one variance is equal to 5. Now I'm gonna throw a question at you, and I'm gonna say, well, obviously they're not equal. Obviously these variances aren't equal, so obviously this is false. Do we agree? Safe ground saying that, so I'm gonna say, look, this is 10, this is 5. Well, obviously this isn't true because this is 10 and this is 5. No, what am I doing wrong? Yeah, this is but you're right. Who says, yeah, that sounds great. Like 10 versus 5? You go home to your 6-year-old, are they different? Yes, they are. Then this is false. Well, wait a minute, what's missing? What's missing from this? One sample, one's population, right? Is everyone on board with that? One sample, one's population. You just snooped on this to tell you something about this. Do you care about this? Who cares about this? Nobody cares about this, right? This is sample data. This is sample data. What you actually want to know is what's going on in the population. So this is only being used to tell you something about this. Make sense? That's the analogous thing to if I put different parameters here. If I put HO and I put mu1 is equal to mu2, and I have mean 1 is equal to 10, and mean 2 is equal to 8, this is the same thing, just different parameters. The first one is the sample variances, the second one is the sample means, but it's the same thing, right? Don't get caught on this good test question, right? Go, I reject the null hypothesis, right? What's your answer? Say, I don't know. Do I reject the null hypothesis? Who says, I don't know? Okay, I got one sample mean is 10. Who would be comfortable making a decision on this and just, okay, so let's look at this. I got one sample mean is equal to 10, and one sample mean is equal to 10. Who says, what's your response? What's your reaction to that? Good exam phrasing, what's your action? I mean, what could I do with this? Ideas. Reject? Not reject? Who says reject? Who says not reject? Who says, hey, I don't know, that's what we got all the theory for, right? Okay, who says gotta do more work? Okay, now why do you say we have to do more work?
Because you can't make decisions of the population based on the sample.
Okay, because you can't make decisions based on the population, based on the sample. What's the deal here? Look. What's the question you ask the question of the data? What's the probability of this difference if what is true? If this is true, right? Well, I don't know what that probability of that difference is. Depends on the variances and stuff like that, right? So who knows? Depends on the variances and the sampling distribution and everything like that, right? They're different in the sample, that's the logic, right? They're different in the sample, but I don't know. Does that suggest what's going on in the population? I don't know, right? What's my t gonna come out to be? What is it? 0. This is one case where you can say, I don't need any statistical theory at all. This is 10, and this is 10. This lines up where with this? Yeah. What's the probability of this given this? Super high, right? Super high. What's your p-value gonna come up to be? Extremely high, right? It's gonna borderline on 1, because you go, well, I've got my 10 and 10. That is, look at the t-test. What happens in the t-test? 0. Do you care what this is? No. That all of this becomes irrelevant if this is equal to 0. And that's the only case, that makes sense? That's the only case where it becomes irrelevant, because right off the bat, that's when you see that, that's a slam dunk. You don't need any inference, you don't need the computer to tell you what to do. You go, there's nothing going on. I already know what the t is gonna come out to be because I know what that numerator is. And somebody comes around, yeah, but what about your standard error? What about your standard? It doesn't matter. This is gonna equal 0. 0 divided by whatever's going on here.
0.
Yeah, it's 0, right? What if but then the person says this, they go, yeah, but I heard sample size and get you a big t value and a little p. Right. What do you say?
Take a Xanax.
Take a Xanax, yeah. After you've said that. So you say, I hear big sample size. I say, you know what, but we've heard that increasing sample size will increase your t, lower your p, so just increase your sample size. Well, there's 2 things that could happen if you increase sample size. What's the most likely thing that's gonna happen if you increase sample size?
You'll get a difference.
You'll probably get some separation, right? That difference of 0 will probably like do this, and eventually maybe you'll get like a small difference. In which case, increasing your sample size, then actually it lowers this sufficiently so that your little difference in the numerator all of a sudden looks big. Let's assume it doesn't. Case number 2, let's assume it doesn't. This stays to be 0. Right? When we say holding constant, so we say, what's the influence of n for a constant difference of 0 in the numerator? So what's the influence of n for a constant difference? The difference in the numerator is not gonna change. So as I increase my sample size goes up, 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 like that. Mean difference, mean 1 minus mean 2, stays at 0 as n increases. What's gonna happen to my t? It's gonna stay at 0. It's gonna stay at 0 because if that's 0 in the numerator, then no matter what you do to n, isn't gonna change that. Yeah.
So even though the nature of that data is still a sample, this is like the only case where you can compare samples to populations?
Well, you're comparing the samples to populations, but this tells you immediately what's gonna happen to that t, because in this case, you know that's gonna be 0. So the standard error of the difference is not of concern because you know you have no difference in the numerator. Right, so look. So this is 10, this is 10. as soon as this changes from anything else to like, let me just go back to the 9. Could be like 9.8, 9.9, whatever. As soon as it changes a little bit, then, yeah, what's the question, right? The question is, well, I have a 1 unit difference in the numerator, so this difference is equal to 1. Yeah, and then what's the question? Saying, well, is this gonna be statistically significant? Is t gonna be large enough? And you say, well, I don't know.
Yeah, what does it look like?
What's going on with the denominator, right? What's going on with the denominator? I've got a 1 point difference. If the denominator ends up being extremely, extremely small, how's t looking? Big, right? If that denominator ends up being very, very small, t is actually looking pretty big. 1 divided by something that's very small gives a big t. On the other hand, if this ends up being quite large, then what's the t ratio actually communicating? It's going, you know what, you got something here, but boy, oh boy, there's so much noise in the population. We would expect stuff like that to happen just by chance. Right? We'd expect stuff like that to happen just out of random variability. The nature of the t, comparing one thing in the numerator to one thing in the denominator, it's kind of like saying, well, how special is this relative to this in the inferential sense. Okay. So that's why 10 versus 9, well, then you say, well, I don't know, what question you ask next. Even if you don't have your stats book, you say, how big was your sample size? What are your variances like? Tell me about the what? Standard error, right? Tell me about the standard error. What's going on in the standard error? Because if the standard error is low, well, maybe that could be statistically significant. If the standard error is large, boy, that could just wash out, right? Same thing, I changed this to, assuming our scale allows it, 10 to 90, same thing. Depending on what the units are, it's the same thing. Let's unpack it. Well, I've got a pretty big difference going on. I've got a pretty big difference. But under what case would this difference not end up being statistically significant? I'm using that word a lot today, right? I don't even like using it, but under what case would this difference not be statistically significant?
If your standard error was like 50.
Right, very big, right? If the standard error is very big, then what's t? You know, when t reports the result, they're saying, you know, you found a big difference, and I know you're enthused about it, but my goodness, how are the waters? The waters are so wavy that when you found, this, that pretty much goes along with everything else. You didn't really find anything, not based on our t at least, not based on our t. But again, we know that what's going to influence the size of t? Well, sample size, variances, and stuff like that. That's why we have to go to the Cohen's d. That's why we have to go to the Cohen's d, which we'll develop a little bit more in a second. Okay, makes sense. So 10-10, the process is the same. We're doing the same thing. It doesn't become a different question. It doesn't become a different question. We're doing the same thing. It's just that automatically we know if it's 10 and 10, ask what's the probability of this difference under this? Wow, it lines up exactly with it. So we're asking the same question. It's just it becomes you don't even need the book when it comes to be equal, and you can think of it as your numerator just doing that. Now the degrees of freedom idea, just to kind of give a little bit of insight into it, is your degrees of freedom. This is based on how many degrees of freedom? N1 plus N2 minus 2. Okay, so that statistic that you're computing is evaluated on a particular degrees of freedom. Now, degrees of freedom, V or DF, same thing. V is often the symbol used for it. Degrees of freedom have what determines degrees of freedom? And what's the determinant here of degrees of freedom? Sample size, right? The sample size determines degrees of freedom for this t-test. Well, let's think about this. If you violated your variances, so we'll talk about how big of a violation here. I mean, if this is twice as large as this, well, no, if I have, maybe this is, 1, very low, well, maybe this is enough for me to say, okay, I think this assumption is false. This variance is so much bigger than this one, then I can assume this assumption to be false. So the rule is generally, and it's a kind of an informal rule, but it works a lot, 4 or 5 times. I think now it's closer to 4, maybe it used to be 5, but 4 or 5 times one variance. So you have one variance here, and you have another variance here, variance number 2. If one variance is no more than about 4 or 5 times the other one, you can generally assume this is okay. These refer to sample variances, not these because you don't have these. But you look at your sample variances, and one sample variance is like 5, the other one is 3, you're fine. Okay. We'll see as well, you can also do different tests. You can do like a Levine's test and stuff like that. We'll do a hypothesis test on it. But just as a rough guideline, that rule kind of works pretty nice. Now, let's assume that you can't do that, that your variances are pretty different. Okay, your variances are pretty different, and you know, this is like 30 and this is 2 and something like that. They're pretty different. Well, the idea behind the correction on the degrees of freedom is the bottom line is these are your degrees of freedom for the t-test. What the correction does, the degrees of freedom for, let's say it comes out to be about 8. Let's say it comes out to be 8 for an example. Your degrees of freedom come out to be 8. You take your t, you evaluate it on 8 degrees of freedom. What's the logic here if the variances are not satisfied? It affects the degrees of freedom. If the variances are not satisfied, there's going to be a punishment. It's a big formula in the book that do the correction on the degrees of freedom. What's the punishment? I mean, what's the nature of it? Let me propose one punishment. I propose that if you can't satisfy your variances, that degrees of freedom should increase. So the adjustment person comes along and says, if you can't satisfy this, I'm going to make your degrees of freedom larger. Calculate your same t, but evaluate on a larger degrees of freedom. What do you think of that? Would that make sense? If we evaluate it on a larger degrees of freedom, is that a punishment for us, given what we know? So what if I said, I'm gonna say, instead of 8, use 10 degrees of freedom. Use 10. Is this bad for us? No, why? Why isn't it bad for us, given all we know, given all the connections? What does 10 degrees of freedom actually have to reflect? So if it goes from 8 to 10, degrees of freedom are computed this way. What's that a reflection of? Increasing degrees of freedom in this case. Increasing sample size, right? Increasing sample size. So, if the punishment person comes along and says, well, 8 degrees of freedom, you couldn't satisfy your variances? Well, then test your t against 10. You say, oh, awesome, this is great. What you just gave me more what? Power. See how the power figures into it? You just gave me more power, that's great. What's gonna happen to your critical t? As it goes from 8 to 10, your critical t is going to go, if you get more power, your critical t that you're evaluating against goes down, It goes down because the test becomes a little bit easier. The test becomes a little bit easier. So that would be a dream. If you violate your variances and you gain more degrees of freedom, boy, we want to violate variances all the time, we do it on purpose. That's not how it's gonna work, right? What's gonna be the punishment factor? The punishment on the degrees of freedom is going to be what? What's it going to do to the 8? It's going to drop it a little bit. It's going to drop it. It's going to say that in words, it's saying, you know what? You've calculated your t, but if you cannot satisfy this assumption of equality of variances, you have no right, literally, of comparing your obtained t to a distribution coming from n+1 and n+2 minus 2 degrees of freedom, 8. This thing that you've computed is not distributed on 8 degrees of freedom. So you should not be comparing that t statistic to a sampling distribution on 8 degrees of freedom. That's literally what it's saying. It's saying this t is not born from such a distribution. It's not born from a distribution with 8 degrees of freedom. So what does the correction do? It's going to drop it down. It's going to drop it down. And if you play with the numbers, you have a slight difference of variances depending on what your sample sizes are and things like that. It's going to drop it down, and it's usually going to drop it down to something that's not even a whole number. So you're gonna see things like this in the software when you do the test. It's gonna be like, instead of 8, it's gonna go like to 7.8 and things like that, like a little bit of a drop. And the drop, is that good for us? It's good for your significance, that's no. It's just a little bit of, it's like a slap on the wrist. We can't satisfy variance, there, we'll get you. Goes down to 7.8. What does it make it harder to do? What does it make it harder to do? A little bit harder to reject the null. It's a little bit harder to reject the null. Gives you a little less power. Gives you a little less power, right? Because you cannot evaluate it on as many degrees of freedom as before. Does that make sense? Yep. Okay, yes.
Sorry, where is that adjustment, obviously you're not changing n or n2. So you just actually choosing a different number for your degrees of freedom?
You're choosing a different number for your degrees of freedom. It's a different way of computing the degrees of freedom that takes into account the unequal variances and just brings them down a little bit. So we're computing the same t, right? We're computing the same t. The t doesn't change, it's just evaluated against a slightly different criteria. And the nature of that punishment, we're gonna see that punishment more when we do ANOVA models and things like that. We're gonna see if you can't satisfy the assumption, always expect to see just the drop in degrees of freedom. So the important issue is the t isn't changing. The t is just gonna be what it is. But you can no longer assume it came from a particular distribution. You have to assume it came from one that is gonna give you a little bit less power. Cohen's d. The other topic we need to talk about is Cohen's d. How big is Cohen's d? Right, that's one of the questions on the assignment is, what's a big Cohen's d? What's a small Cohen's d? And we could also talk about that in terms of the eta squared, now that we're getting into the effect size for eta for ANOVA, we'll talk about that more. But we have Cohen's d, okay? How big is big, right? How big is big for a Cohen's d? Well, let's think of some scenarios here. Let's think of, you get a Cohen's d of equal to 0. Let's take care of that first case. Your Cohen's d is equal to 0. What's that telling you? What's that telling you? Well, that's telling you you have nothing going on in the numerator. What's your effect? It's 0, right? It's 0. You have no effect. You have no effect. So kind of like that equality of mean sample variances, you see a Cohen's d of 0, you're not saying, well, how big is that? That's 0. There's nothing going on. You have no difference. You have no difference. In the case of two means, there's no difference between the means. You're not going to ask the researcher, you're not going to say, yeah, but what's your standard deviation? You're going to say, well, there's nothing going on, 0. Okay. So after we've taken care of that, let's take care of the case of a Cohen's d of, well, let's put it as an open question first. What's a big Cohen's d? What's a big Cohen's d? And we could ask the same thing about eta squared. Now that we know eta squared, what's a big eta? SS between over SS total. That's total. Might be easier actually if we look at it in terms of eta. Even though the question addresses Cohen's d, let's just talk about it in terms of eta for a second, because it makes more intuitive sense with the proportion idea. So eta squared, we said what can range between what? 0 to 1, 0 to 1. And we talked about why that's true, right? Why that's true. So when do you say, wow, eta is big? Well, let's take care of the obvious cases. If it's 0, pretty small. What does it, eta squared of 0 mean? Well, when you look at this, how do you get an eta squared of 0? 0 over SS total. This expresses mean separation. Whatever the denominator is just reflects how much variability you have in your data. So if somebody walks around the department saying, I got an eta squared of 0, we go, you got no effect. You got nothing going on. Right? No, you don't have to say, well, is that big? That's not, you got nothing. What if they get 1? right? If they get 1, then what's that? What's the only way that happens? SS between is equal to SS total, right? So that would be that highest value it could be, and we can see with the justification for why those limits must exist for that. You can't have an eta squared greater than 1, because you only have 1 sandbox to play in. This has to be a subset of it, right? It has to be a subset. And even a subset, mathematically speaking, could be equal to the set. So this has to be a subset of this, and the subset could actually be equal to the set, okay? So SS between over SS total. So 1 would mean what? It would mean 100% is explained, right? 100% is accounted for by group separation. 100% is accounted for. So between these limits, 0 to 1, we got this one. We know this one we're fine, this one we're fine. How big is big? And again, we'll just go with eta squared for right now. How big is big? So, the case scenario, somebody comes up, walking outside, and they say, I have an eta squared of 0.80. It's like water cooler talk. Talking to the water cooler, say, did an experiment yesterday? What'd you get? 0.8. I got an eta squared of 0.80. National's gonna win, probably. You got an eta squared of 0.80? Say, interesting, right? And then they say to you, well, you took the stats class, and how was that? The researcher asked you that. Is that big? Is that small? I got an eta squared of 0. I was doing some stuff in chemistry, and I got an eta squared of 8.0. Is that big or small? And you're coming from the stats class. What do you say? So, and they're asking you, so they're, in this case, you're being the statistical consultant. They're coming from chemistry, and they're saying, I got 80%, eta squared of 8% in my ANOVA. They're saying to you, hey, how do you assess that? Here's the best answer. You're gonna love this answer. You're gonna love it. What would you say? They say, hey, you're the stats person, how would you assess that? This is the one time in your life that you're able to punt it right back into their corner and feel totally good about it. They say, how big is that? You go, I don't know. How big is it? And you're perfectly correct. You're perfectly correct. They cannot blame you for being a smart ass. You're completely in your rights to say that. No, why? So, how big is 0.8? You say, I don't know. How big is it? Why? Why is that the only response, unless you are the chemist too? If you're the chemist too, if you're a chemist doing the same kind of research that they're doing, then maybe you could have been more helpful. But otherwise, if you're the stats consultant and know nothing about chemistry, and they say, I mix this, I got an eta squared of 8.80, why is your only response? In the big picture of things, they would say, I don't know. Is it? And then you can even get on them about that and say, you don't know whether that's a big or a small effect size? Shame on you. Why? You can even make them feel bad about it, almost, right? I'm just kidding, don't make people feel bad. But what is it about that? We don't know how big it is. You don't know how big it is. I don't know how big it is. And that's, I say that a lot. How big is my effect? I don't know. How big is it? Why? What's the only way I would be able to know, or you'd be able to know, as the stats consultant, as to how big that is?
Past experience.
Past experience. That's why you say, well, I don't know. How big is it? And then the person, I have no idea what you're talking about. The person says, then give them an assignment. Give them an assignment. What assignment do you give them to do? What do you tell? You say, go learn your area of research. Go learn your area of research and find out what's going on in your field. So 0.80 is not determined on a p-value basis. It's not determined inferentially. Okay, so this is not determined inferentially it is determined by research knowledge. Okay, it's determined by research knowledge. So here's the scenario. Is 0.8 big or small? Can you give an example of when the answer would actually be it's big? While 0.80 accounts for 80% of the sums of squares, if what? If everybody else is finding this, then that looks pretty big, right? That's pretty big. So if every other cancer treatment is explaining this much, and yours is explaining this, that's pretty impressive. When is it meaningless waste of grant? Well, not a waste of grant, but when is it like, no, you're not gonna cure people with this, or it's not gonna help us? When is it a low ball? When everybody else is getting 99. So when you look at the articles in your field, the other researchers, or communications by email, or knowledge of who's, you go to conferences and you hear effect sizes of 99 floating around, then you know that your 0.80 is actually quite low. That's how you determine the size, the magnitude of effect. It's not statistically, it's determined relative to the research area. Okay, so if we look at, a lot of psychology experiments, if we're lucky, they explain 30%, 40%, right? It's really tough. There's a lot of variability, it's really hard. So if you get one of 60, that's actually pretty good. Now, if you look in physics and you walk around bragging about your 80%, about what the stuff does in the collider and all this stuff, right? They're gonna go, if you're explaining 80%, you're probably even doing the experiment wrong, right? Because we can explain a lot more. Or like a medication, maybe the medications, maybe they're somewhere in the middle. Maybe aspirin only explains 70% of the variance or something like that. So if you develop a medication that explains 80% or 90%, that's so much better. Okay. So it must be determined relative to the research area. You can say, for instance, once they go to 0 and once they go to 1, that it's pretty big, but these should not be assessed. These should not be assessed in terms of absolute value, unless it's 0, 1, then it's obviously very big or very small, right? But even if you get the 9.9, well, if everybody else is finding 9.92, well, then you're right in line with everybody else. So all of a sudden it becomes average. It's like, wow, this is big, but it's actually average relative to the research area. All those things should be kept in mind. The best thing to tell your committee at defense is, after you report your p-value, you give them your effect size, but always take the responsibility to tell them if it's big or small. Tell them. Be the researcher. You're the knowledgeable one. Say, I got an eta squared of 0.80, and that's actually pretty impressive, because most other people are finding 0.60. This is the highest we've seen in a while. Or tell them, most others are finding 0.90. So the 0.80 actually isn't that impressive. Notice, right, it's easy to fool people with statistics, because if they don't know the background, in this case, if they're not the scientists in the area, then if you start looking at just the mathematical magnitude, well then 0.80 is actually pretty high. But these are not abstract numbers, not the way we're using them. We're using them to describe real things. So you have to be aware of that.
Is it the same for Cohen's d now?
It's the same idea for Cohen's d. Okay, it's the same idea for Cohen's d. Cohen's d is not bound by 0 and 1. It can actually be bigger than 1 depending on your mean difference. But if you look at your mean difference, I mean, if this comes out to be 2 or 3, well, technically speaking, that's getting up there. I don't know the exact conversion. You can convert those to R² stats, but that's getting to be, pretty up there. But again, the same idea is if it's normal in your field to find Cohen's d of 5, well then, all of a sudden your 3 and your 4 is actually not that impressive relative to the area. Cohen's guidelines. Yeah, you've heard of Cohen's guidelines. Cohen's guidelines, Jacob Cohen, the person who stole this from statistics and called it something else. This was always known as statistics. He took it and called it Cohen's d. It's the standardized statistical difference, and it's always existed. He gave guidelines of something like, I forget what they are, cause I purposely don't memorize them, cause I think they're kind of foolish, but it's about 0.3, 0.5, 0.8. And use those, say, if you're at 0.3 or less, this is a low effect, this is medium, and this is large and increasing. And if you convert those to eta squared, you'll find some pretty healthy percentages, but that's not the way to evaluate effect size. This is maybe how the aliens would evaluate effect size. If they had nothing else to go by, they would just look at the raw numbers and say, well, that looks pretty big. But know your research area, read your literature, the history of what you're doing too, find out if your experiment has been done before. Know that really well, so you become really knowledgeable of what effects you're seeing, what effects you're reading. You come across an article, and they say, we found something. I say, nah, not really, that's not very impressive. That's not gonna come from statistics, that's gonna come from your knowledge and research area. So you're saying to the chemist, you're saying, go back and check your research area, because I can't tell you unless I'm a chemist. Okay, let's see, why don't we take a little bit of an early break? This serves as a nice place to stop. Take a little bit of a break, and we'll come back and we'll do a little bit more ANOVA, and then we'll start talking about the job. I have a few assignments here too, and I'll talk about those when we get back.
Amy.
Yes.
Let's go. Yay.
Is it the third? Is it the third from the little key?
It's the third.
Did you have